I'd just like to introduce our next speaker, Nicolle Eagan. She works in the office with us. You may have seen her speak at one of our meetups last year. She's from Buffalo, so she'll give you all the good, Buffalo wings recommendations in New York City, where's good and what's real and what's not. And she's going to talk today about the exploration of the solar systems. So this is the NASA Frontier Development Lab project that we did, I think it was last summer. So over to Nicolle.
Thanks, Fenton. The answer is there are no good chicken wings in New York City. You have to go to Buffalo for them. So, my name is Nicolle Eagan. I'm a data scientist at KX. And last summer, I was honored to have the opportunity to travel to California and work at the NASA Frontier Development Lab. And I'm going to be describing the work I did with them and also what I've done since then to enhance that work. So just to give a bit of background, Carl Sagan, who I'm sure you've all heard of in history, he was a really, really famous astronomer in the 1900s, and he was famous for doing research on extraterrestrial, which is why ET is in my PowerPoint. And of the many, many achievements that he had throughout his career, one of them was that he co-founded the Search for Extraterrestrial Intelligence Institute, known as SETI, which is based in Mountain View, California. In addition to doing research with extraterrestrial life, they also try to promote research and education within the space sciences in general. So a few years ago, NASA decided to host the Frontier Development Lab, or FDL, at SETI. The Frontier Development Lab is a research accelerator that tries to take the bleeding edge AI technologies and use them to solve challenges within space sciences. So one of the teams last year at the Frontier Development Lab was the solar storm prediction team. To sort of explain what a solar storm is, in 1859 there is something that happened called the Carrington event. So the sun emits two different solar storms. One is just a solar flare, but the other is called a coronal mass ejection. And when that solar storm is emitted from the sun, it can disrupt any magnetic sphere in its path. And that's what happened in 1859. A coronal mass ejection hit the Earth. And at the time, there was only telegraphs, but it did render telegraphs completely useless for a few days. So if a storm of that magnitude were to hit the Earth today, GPS would go useless, cell phones would be down, and since I'm a millennial, that's pretty much life-ending for me. So it's really important that we solve this problem. So the solar storm team came up with a tool called FlareNet, which is a long short-term memory recurrent neural network, or time series analysis neural network. And what they decided to do is say, given the current state of the sun at this time, at which point in time will we see a solar storm and how strong will that solar storm be? So you're probably wondering at this point, why KDB+? Well, this is a time series analysis neural network, and we are the best at time series database analysis. Also, I'll get into the data a little bit later, but these solar storms do travel at the speed of light, and since KDB+ does have nanosecond precision, we're among the best to be able to sort of capture these things as closely that we can to real time. So the data. So throughout the world, the U.S. Geological Survey has data centers set up that take in readings from the sun. I'm only going to focus on 14 of them that are in the U.S. So as you can see by the diagram here, there are 4 readings that each data center takes in. They're based on the XYZ vectors and also the F vector, which just points to the XYZ coordinate in space. They refer to these as channels, so that's how I'll refer to them. And each data center collects a reading for every channel for every minute of the day, which isn't a lot, but over many days, months, and years, it really adds up to be millions and millions of rows, which KDB can handle quite easily. So while I was at FDL, I built a database for them, and I decided to run some basic queries to show them the power of the technology. But since then, KX has taken a lot of steps to do some initiatives outside of just the language. And so for this talk, I decided to use JupyterQ. So it takes about 20 minutes to set all of this up. I was set up with a Google Cloud instance using 8 Intel Skylake cores, 50 gigs on disk and 50 gigs of RAM, which is pretty good for the amount of data that I used. I also utilized the 64 on-demand version of Q, Anaconda, which is for version 3.5 or higher, and EmbedPy. If anyone in here doesn't know, EmbedPy is part of our Fusion initiative, and it basically allows us to call Python libraries from KDB+. So it's a really, really good tool that we're able to use. And when you put all of that together, you get JupyterQ, which is our kernel, KDB+ kernel that we now have embedded in the Jupyter notebooks, which is really, really exciting. So without further ado, here is my notebook. So the first step, obviously, is to read the data into KDB and create the database. So the USGS has a GitHub repository, the GeoMags algorithms repository, which you can Google and find quite easily. And that holds algorithms that utilize Python to scrape their website and download all of the data. So I was able to do that, and the data downloads as pickle files, which an FDL participant last year had a quick Python script for me to be able to transform those pickle files into CSV so I could read them into KDB. So that's what I did. First, I just defined the data centers as symbols that I'm going to use as a column. And when I originally read in the CSV file, that's what it looks like. So we have a column for every data center, and then the readings are the entries in the column. But as we have this wonderful time series database, I wanted to save the data in a different way. So I decided to do some manipulation. As I already knew the readings were going to be for every minute of the day, I can do some really quick arithmetic and be able to get all of the times for the entire year of 2016. And I picked the year 2016 in particular because it was the year that the FlareNet team used as their validation set. And so with just a few lines of Q code, but not a while loop, I was able to, sorry, there's some adverbs in there, it's pretty good. I was able to create my database just with 3 columns. So we have the time, the data center, SIM in this case, and the reading, and then save that down to disk. So now that I have my data, I can start querying it. So just to give a breakdown of the tables, I have 4 tables. One, they're for the year 16 and then the channel that the reading was from. So that's how I decided to organize my database. So the first thing that I showed everyone at FDL was just how do I query the data? How do I get some basic statistics? So the first thing I wanted to do is just for all the data I had, get the standard deviation and the average reading by date and data center, which didn't take that long at all, just over a second. And I was able to get some basic statistics, so that was really nice. Another function, which I'm sure you're all familiar with, is deltas. And the reason why I thought this was good is we can immediately see where the biggest changes in readings are, whether they're positive or negative, which would give insights to days where maybe the sun readings were more volatile than others. So you can see here that there's some dates that appear towards the top. I've organized it by the magnitude of the readings. So July 19th and March 13th and July 20th appear quite a bit here. So those, to me, struck out as days of interest that I could examine further. But since I am working with a Jupyter Notebook here and I have the power of EmbedPy, running queries is great, but I wanted to be able to visualize some of the results that I had. So I leveraged some libraries in Python. So I leveraged NumPy and Matplotlib, which I'm sure most of you have heard of. I also used Basemap, which is a geological plotting library in Python, and Seaborn, which is one of my favorites because it's a high-level interface to Matplotlib, and you can generally make plots with 1 line. So for Q coders, that's a huge plus because we don't like, loops and multiple lines of code. So the first thing I did was I just grabbed a reading from the X channel for one of those days in question, and I just happened to pick Tucson, Arizona as my data center. And with using EmbedPy, I can call .p.set, which basically takes the data stored in the Q variable and sets it to a variable in Python. And it sets it as a NumPy array, which is perfect because then with 1 line, I can plot a really nice distribution of that data. And I actually thought the distribution was pretty interesting because it does look normal, but there's a lot of data at the left tail there, so that's something to definitely look into. What I wanted to do too is compare Q code to Python code. And so for those of you that don't know, the EmbedPy team has built a Q wrapper around matplotlib, so you can call Python code. You can call Python basically in a Q syntax sort of way. So to do that comparison, the first thing I did was wrote a function that just normalizes all of the readings for a particular day for all of the data centers, and I put them to Python as well. So the first thing I did was just wrote some Python code using a nice for loop to be able to plot all of those readings. And you can see the graph there. I actually thought this was interesting. There's a lot of variance at the beginning of the day, which makes sense because as the sun comes up, the sensors are going to pick up a lot of data. But I would have expected that too at the end of the day when the sun goes down and it gets dark again, but we don't really see that sort of variance. So I thought that was quite an interesting find. Then I made the same graph with the Q wrapper. So you can see that we basically initialize the plotting here. And then instead of using a for loop, I basically just use each with a quick little function to plot each of the lines. And then the nice thing too is you can see here, I have to basically make a list of all the arguments. But because this is Q, I just have a simple, well, there's two ways to do it, but I have a simple dictionary here that just reads in all of the arguments. And you can see that the plots are exactly the same. They render at about the same time, but if you're not super comfortable with Python code, and want to use Q, this is a more Q-esque way to do it. So that was cool, but I really wanted to use some geographical data because we are dealing with data centers around the world and the sun and all of that. So I decided to use the base map library, as I said. There's reference data on the GeoMags website that allows me to pull the latitude and longitude for all of the data centers. So the first thing I did was just simply plot it just to see where they are. And I thought it was pretty interesting that there's a lot of data centers relatively in Alaska as opposed to the contiguous 48 states. So I thought there had to be a reason for that. So the next thing I did is wrote a function in Q that says for a particular channel and day, just give me the maximum readings for every data center. And so I did that below for May 2nd and plotted a heat map for those data centers, which I thought was extremely interesting because you can see that the closer to the equator, the less the maximum reading was for the day. And as we go north towards Alaska, the readings are quite stronger, which struck me as odd because I kind of assumed in my head, well, if locations are closer to the equator, the sun must be stronger because it's warmer, which was not correct because then I thought the Earth is tilted on its axis, so actually, like physically speaking, Alaska at times would be closer to the sun, which in my mind explains the heat map that I'm seeing there. So obviously there's a lot more that you could do with the data. This is just a small varied example to show the sorts of things you can do not only in Q with non-financial data, but also using the power of JupyterQ and specifically EmbedPy to get some plots and make some insights there. Cool. I just want to acknowledge the Study Institute and the Frontier Development Lab for hosting me last summer and letting me work with their researchers. And I also want to acknowledge Fintan and Abby for supporting me through this and allowing me to do this presentation. Thank you. My notebook is posted on my GitHub page, so if you want to take a further look at some of the coding examples I had, feel free. Thanks.